Hello my dear friends, welcome to my YouTube channel. Today we will discuss about the most important topic, that is organic field effect transistor. This is the new area of specialization. Many researchers from different countries are working on that. Let's start. Organic field effect transistor. In this presentation I will cover the following topic. The first topic I will cover why organic field effect transistor is needed. Second, a brief history of organic field effect transistors. Next is why carbon is so special element in organic field effect transistor. Next is major classes of organic semiconductor. Next, organic field effect transistor fabrications problem and their solution. Next, effect of gate dielectric thickness and semiconductor thickness on device performance of organic field effect transistor based on pentacene. Next is top contact and bottom contact organic field effect transistor. Next, I will show you the proposed organic field effect structure parameter. Next, we will discuss about in the Silvaco how to design organic field effect transistor, top contact organic field effect transistor in Silvaco TCAD ATLAS tool. Next, I will show you top contact and bottom contact structure. Next, I will show you compare the transfer characteristics of top contact and bottom contact devices. Organic field effect transistors have grown on research area over the past 2 decades. Most of the advantages in organic field effect transistor is low thermal budget required to fabricate these devices and their high degree of mechanical flexibility. These characteristics follow from the two basic properties of organic semiconductor. Organic semiconductor enjoy semiconducting properties on the molecular level. Second property is bonding between organic molecules can be weak, usually formed by van der Waals bonds. Because no covalent bond need to be broken or reformed, organic semiconductor material can be manipulated using a small energetic input. The weak bonding and ease of manipulation often comes at some price in performance. So let's start a brief history of organic field effect transistor. The metal oxide semiconductor capacitor using organic semiconductors was demonstrated by Ibswa, Kurokawa and Nara at NTT in 1982. The device was fabricated using polyacetylene as the semiconductor on a polysiloxane gate dielectric and used aluminum for the gate and the gold is used for the source and drain electrode. The author clearly recognized the concept of potential and ended in the paper suggesting that this type of device appearing promising for the thin film transistor. The next significant milestone was the development of first organic field effect transistor with recognizable current gain by in situ polymerized polyethylene transistor by Tsumba and Kursaz in 1986. Interest in organic semiconductors began to intensify in late 80s and early 90s, in large part because of a report of organic field effect transistor, an organic heterojunction organic cell by Tang in 1986 and organic light emitting diode by Tang and Mansukhli in 1987. A number of programs were established at academic and the industry research center to investigate one or more of these device architecture. The first OFET device was fabricated by directly polymerizing insoluble film of polystyrene and polyethylene onto substrate, which is a technique that is limited in its large area of applicability. A soluble form of polyethylene developed by engineers and applied to the organic field effect transistor later. It remains one of the primary goals of the organic field effect transistor research community to develop applications which uniquely exploit the properties of organic field effect transistors and translate them into the killer application which will cement organic FETs relevance and exploit their unique characteristics. This slide gives a summary of chemical physics of organic semiconductor operation. It explains why carbon is so special and how its unique properties lend it to the formation of an unusual class of semiconductor material. Carbon has a relatively small size, This reduces the steric hindrance in carbon-containing molecules and allow a large variety of compounds to be created. Carbon has a moderate electronegativity. This allows it to form covalent bond with virtually all materials, including other carbon atoms. Carbon is a group 4 material. This allows it to form 4 bonds, increasing its chemical versatility and helping it to form long-chain polymers. Carbon hybridizes in a number of forms. This allows for a wide variety of bonding configuration, including single, double, and triple bonds, as well as a range of resonance forms. Because of these properties, that both synthetic organic chemistry and natural synthetic processors are able to deliver a wide range of carbon-based materials. So that the carbon is the basic element of the organic materials. Organic field effect transistors have unique material properties, which both make them attractive as a material system and somewhat complicated to handle. A difficult question in which organic semiconductor material is best to start with for a device application. There is no single answer for that, but several considerations should be made, including: first one, what mobility, threshold voltage, and ion-IF ratio are required. Second, what materials are commercially available in a suitable form. Example in solution, powder, etc. Who will purify the material? Is it possible to purify internally or use third party? Is the material compatible with the desired electrodes and gate dielectric? Is it important for the material to lack a strong photocurrent response or fluorescence? Is the material stable and a facility available for handling and packaging non-air stable materials? In this slide, I will explain the major class of organic field effect transistor materials which are in use, their properties, and some of the advantages and disadvantages of each system, in which I also discuss many of the parameters and doped organic conductors which can be used as an electrode. Organic semiconductors are generally small molecule or polymers made from a small fundamental group or conjugated monomer units, polymer semiconductor and small molecule semiconductor. I am not going to the details of polymer semiconductors and small molecule semiconductor. If you need more information about this, you have to follow the books. There are various books of organic field effect transistors are available online. Please go to the books to understand more about these materials. There are various factors in which OFET fabrication depends. First one is the source and drain electrode. One of the critical operating junction in organic field effect transistor device is source and drain contact to the channel. The source and drain electrode formation and structure can also influence the properties of the transistor channel itself. Work in the source and drain contact, we will cover the following topic: work function consideration, top versus bottom contact, treatment of contact, creation of lithographic top contact devices. The next factor, gate dielectric. I will cover the following topic: characteristics of gate dielectric, crystal structure improvement, self-assembly monolayer gate dielectric, introduction of surface dipole, functional gate dielectric. Next is air sensitivity and encapsulation. Next is emerging deposition and patterning processes, in which I will cover laser-induced thermal imaging, organic vapor phase deposition, surface energy modulation. Alternative OFET design are available: static induction transistor, reduced patterning processes, electrochemical OFETs, self-aligned organic field effect transistors. In the work function consideration, an additional consideration in the selection of source and drain electrode is the work function difference between the semiconductor and the energy level in the semiconductor. Gold is a popular choice for P-type field effect transistors, since its large work function provides reasonable access to the HOMO level of many materials. There are some indications that noble metals like platinum with a high work function may provide even better contact performance. These are the three energy bands. First one is a crystalline semiconductor, second one is metal, third one is organic semiconductor. You already knew about the crystalline semiconductor and the metal energy band. In case of metal energy band, work conduction band and the valence band are overlap each other. In case of organic semiconductor, the two most interesting molecules orbital are the frontier states, the higher occupied molecular orbit HOMO and the lowest unoccupied molecular orbit LUMO. LUMO. As the molecule increase in size, the HOMO and LUMO gap decrease in magnitude and it becomes easier to generate a excited state. By engineering the electron energy level of organic semiconductor, it is possible to set the HOMO and the LUMO level so that the equilibrium potential at no bias sites in a region which is thermodynamically stable against the redox reactions. For p-type material, experiments have shown that the HOMO needs to be lie more than 5.2 volt below the vacuum level. Next is the top versus bottom contact. In the top contact, the metal is on the top of the pentacene, and in case of a bottom contact, the metal is in deep of the pentacene material. Pentacene is basically a organic field effect transistor material. In addition to any enhancement caused by the local damage during evaporation, the structure of the crystal at the source-drain interface can be complicated by the presence of a metal when depositing small molecular semiconductor material. When the molecules are deposited on a metal, especially a noble metal like gold, which has no oxide on the surface, the electron cloud in its lowest potential energy configuration facing into the metal layer. This makes small molecule lie down on the substrate at the source and drain contact in a different configuration than that observed in a channel. A schematic representation of molecular packaging, top and bottom contact OFET device are shown in the figure. Small molecules deposited on the metal contact tend to lie at and do not have a contiguous grain structure where the molecules are standing vertically at the center of the channel between the source and the drain contact. Next is treatment of contacts. Treatment of contacts. Many process flows require a bottom contact electrode configuration. For these processes, one solution to the bottom contact problem is to treat the contact to improve the device behavior. One method to engineer the condition of the surface selectivity is to use self-assembly monolayers. Creation of lithographic top contact devices. Most lithographic processes require bottom contact devices because the semiconductor used cannot tolerate exposure to the process chemicals which would be required to create top source drain contacts. It is now possible to lithographically define top contact on material which has been deposited on a favorable dielectric for semiconductor growth and achieve superior device performance. Top contacts may also be advantageous because of the improved contact through the damage layer created when the metal condenses on the surface. It is also possible to create top contact devices using printing processes. Next is the gate dielectric. As with the source and the drain electrode, the composition and the condition of the gate electric plays an important role in the performance of the organic field effect transistor devices and can also affect their functionality. Characteristics of gate dielectric. A large variety of the material have been used as organic field effect transistor gate dielectrics. A number of considerations go into the process of selection of gate dielectric. It has minimum leakage current, patterning convenience and compatibility, semiconductor compatibility, achievable capacitance, surface tunability, and hysteresis. Hysteresis in organic FETs can arise from number of sources, such as by using ferroelectric material. Organic gate dielectric with strong polar groups can absorb water and experience a slow relaxation which can compromise device performance. Next is the crystal structure improvement. In bottom gate devices, in addition to insulating the channel, the gate dielectric is also the surface which templates appropriate growth for the semiconductor material. It is possible to improve the growth of the organic semiconductors on gate insulated material through appropriate surface modification. Next is self-assembled monolayer gate dielectric. Another application of self-assembled monolayer gate dielectric to organic field effect transistor is the use of insulating high quality SAMs as the gate dielectric. Because SAMs are only one molecular thick and self-limiting. It is possible to create almost perfect low leakage insulator with high capacitance through careful engineering of the surface condition and application of the same. This high gate capacitance makes it possible to achieve very high conductance device with low leakage current. Several high performance integrated circuits have been demonstrated using this concept. Next is the introduction of surface dipoles. It is possible to engineer surface dipoles at the gate dielectric interface to manipulate the charge carrier density in the channel and change the effective threshold voltage of the device. This is achieved by placing an electronegative or electropositive material at the gate dielectric surface, which donates or withdraws a charge from the device channel. A schematic representation showing the dipole formed by the treatment of gate dielectric with an electronegative species. Even though the total dipole is electrically neutral, the process releases positive carriers into the channel and shift the threshold voltage in positive direction. Negative charges can be introduced instead using an electropositive treatment. This shift in the threshold voltage can be seen as a capacitor integrating potential over the length of the dipole. No net charge is introduced in the picture. Next is the functional gate dielectric. Another consideration for the gate dielectric is selecting material which provide interesting device functionalities. One functional gate dielectric of interest to a number of groups is using a ferroelectric material to retain state in the transistor devices. This has a range of applications including latching circuit and memory storage elements. Next is the air sensitivity and encapsulation. Many organic semiconductors are not stable against exposure to oxygen and the water. Several strategies have been developed to remove these elements from organic semiconductor layers and seal against their penetration. Perhaps the simplest strategy is to eliminate a plastic sheet on the top of the transistor with a suitable adhesive. It is also possible to coat organic field effect transistor with a layer of perylene, Teflon or other compatible polymer and optionally seal the device using a metal vapor barrier layer. This will helpful for air sensitivity and encapsulation process. And the last one is emerging deposition and patterning process. First one is the laser induced thermal imaging. Second one is organic vapor phase deposition, and the third one is surface energy modulation. Next is the effect of gate dielectric thickness and semiconductor thickness on device performance of organic field effect transistor based on pentacene. In the proposed structure, we will study the effect of gate dielectric thickness and the semiconductor thickness on device performance. In this lecture, the pentacene based organic field effect transistors with aluminum as gate dielectric were simulated, and the effects of gate dielectric thickness and semiconductor thickness on device performance were investigated. The device performance depends on the thickness of the active layer non-monotonically, which can be explained by the morphology of the pentacene film and the position of the conducting channel in the active layer. The device with the pentacene thickness of 30 nanometer shows the best performance. Recently, organic thin film field effect transistors have caused more and more research interest because of their properties of flexibility, low cost, eco-friendliness, and ease of processing on a wide range of substrates at low temperature. Organic field effect transistors have potential application in flat panel display, low-end storage element, sensors, and integrated circuits. Next is the performance of organic transistor is defined by several significant parameters, including drain current, mobility, threshold voltage, ion-IF ratio, subthreshold slope, and the contact resistance. Understanding of morphological ordering of the semiconductor layer and the interface between the layers are extremely important factors in improving the device performance with respect to change carrier transport mechanism. When you simulated organic field effect transistor, ordering of semiconductor layers is very important because it can improve the device performance in terms of charge carrier transport mechanism. One of the main issues related to these effects is the dependence of the device performance on the semiconductor and dielectric thickness that could significantly alter the device characteristics. In principle, the charge carrier accumulate at the organic semiconductor dielectric interface within a few nanometers in semiconductor, eliminate the role of rest of the bulk semiconductor in the current conduction. Next is, ideally the thickness of the semiconductor should not affect the device parameters. However, several researchers have reported its effect on the performance of organic thin film transistor with a variety of semiconductors including pentacene, P3S3 and etc. Thickness of the active layer is not the only factor that affects the organic field effect transistor electrical parameter. Dielectric thickness is also a crucial influencing factor. Next is, a decrease in the thickness of the dielectric layer results in a significant reduction in threshold voltage due to a high gate capacitance. Lower threshold voltage is useful in reducing the device power consumption and is therefore beneficial in producing portable device. If you are reducing the threshold voltage, you can scaling the device further. This will beneficial in very large scale integration circuit designing. There are two types of organic field effect transistor structure. First one is the top contact structure and the second one is bottom contact structure. In the top contact structure, the source and the drain metal electrode is on top of the organic semiconductor layer. But in case of bottom contact structure, the drain and the source metal electrode is in bottom of the organic semiconductor layer. In addition to this, the mobility also increases with reduction of dielectric thickness. Moreover, the mobility of studies are based on top contact structure only. However, the impact of layer thickness is also based on device structure due to charge carrier transferring on distinct path between the source and the drain. As a result, the thickness of layer affect the organic field effect transistor behavior differently while it realizing in top contact and the bottom contact structure. The top and the bottom contact structures are differentiated on the basis of contact resistance due to their dissimilar architecture and different charge carrier injection area. Figure shows the schematic representation of top contact and bottom contact organic field effect transistor structure showing X and Y distance along the organic semiconductor layer. Important point to be noted before going to the Atlas TCAD code. This lecture emphasizes the impact of semiconductor and dielectric thin layer thickness on the performance of both the top and the bottom contact structure in terms of various electrical parameters including drain current, mobility, threshold voltage, I/O/IF ratio, subthreshold slope and the contact resistance. The thickness of the semiconductor primarily affects the on current. However, off current also rises with an increase in the thickness of the organic semiconductor layer due to increase in the bulk current. A large magnitude of the off current increases power consumption and add to the charge leakage through the device that limits switching behavior of the device. This is the device parameter for top contact and bottom contact organic field effect transistor structure. Primarily, electrical characteristics of top contact structure are validated through device dimensions given in the table. Afterward, the bottom contact structure is analyzed with the same dimension and we will compare the result of both top contact and the bottom contact structure. The conducting channel is formed through pentacene P-type organic semiconductor material with the length and the width of 10 and 100 micrometer respectively, whereas aluminum dioxide Al2O3 is of use as a dielectric layer of having thickness 5.7 nanometer. The other parameter of the device possesses a 30 nanometer thick film of pentacene as semiconducting active layer. Pentacene device show a high field mobility of up to 1 centimeter square per volt second. Aluminum was chosen as the gate electrode material of thickness 20 nanometer. A 20 nanometer thick layer of gold is used as a source and drain contact electrode. As I have already mentioned that the thickness of the organic semiconducting layer is 30 nanometer and the material is pentacene. Thickness of the dielectric layer is 5.7 nanometer and the material is Al2O3. Thickness of the gate electrode is 20 nanometer and the material is aluminum. Thickness of source and drain contact is 20 nanometer and the material is gold. Channel width 100 micrometer and the channel length 10 micrometer. This is the structure code of top contact organic field effect transistor, starting from the command go atlas. In the structure, first I defined the meshing in the x direction as well as the y direction. Next is the region number 1 with the material pentacene with their positional parameter. Region number 2 with the oxide layer Al2O3 with their positional parameter. Region number 3 is air with their positional parameter. Next is the electrode material. At the top of the organic material, at the drain side and the source side, we are using the gold material, and electrode name 2 contains aluminum material at the channel region. The gate material comprised of aluminum material with their positional parameter. This section defined the dimensions of the individual layer along with the position of the electrodes. The layer of the insulator and active organic materials are defined. The source drain contact in top contact structures are positioned at the top of the organic semiconducting layer, whereas in the bottom contact structure, the contacts are placed in below the organic semiconductor layer. After defining the structure layers with the appropriate dimensions and material, individual simulation domains are divided into a finite element grids that is called meshing that comprise a complex grid of triangles. At these discrete grid points, the model entails the calculation based on elemental device physics equation related to electric field, electric potential, and charge carrier density. The accuracy of the simulation results depend upon the density of the fine mesh at the critical points like junction or interface of different material. The placement of the mesh with high density is required in the structure. The next section defining material parameter and application of appropriate physical model, in which we have defined the doping at the region number 1 is uniform with the concentration of 3 into 10 raised to power 17 p-type material, and the material name is pentacene. Next, I have defined the material pentacene with their different parameter: energy band gap, density of the electron, and the density of the hole, permittivity, mobility of the electron, and the mobility of the hole. Next is the material name Al2O3 with their permittivity 4.5. Next, I have defined the contact name, source, gate, and drain with different work function. At the source and the drain end, we are using the gold metal, and at the gate, we are using the aluminum metal. Next, I have defined the organic defects with their different parameters. Next, I have defined the mobility parameter, model statement. Next, I am using this command to retrieve the energy band diagram, potential, and electric field from the structure file. Next, I have saved the file and observed with the help of Tony plot command. This section of the simulator described the physical model to predict the results with proper boundary conditions. It included the Poole-Frankel mobility model that effectively evaluate the static and dynamic behavior of the device and the circuits. This model includes the Hall and Poole-Frankel factor are specified by delta H and beta H respectively, and gamma is used as a fitting parameter, where NTA and WTA are the effective density of state and characteristics energy width of the exponential trap distribution respectively. EC refer to the energy level of the bottom of the conduction band. The organic defect statement includes various electrical parameters such as band gap, electron affinity, permittivity, and effective density of state in both the conduction band NC and the valence band NV. Effective density of state in conduction band is represented by NC, and the effective density of state in the valence band is represented by NV, and are assumed to be of the order of 10 raised to power 21 per centimeter cube. Zero field mobility and relative permittivity of pentacene are 0.5 centimeter per volt second and 4 respectively. This means zero field mobility has the value of 0.5 and the relative permittivity of pentacene is 4. Pulle-Frankel model parameter delta E and beta are 1.792 into 10 raised to power minus 2 and 7.758 into 10 raised to power minus 5 electron volt, and the value of delta E is 1.792 into 10 raised to power minus 2 and the value of beta H are 7.758 into 10 raised to power minus 5 electron volt. AE is the activation energy of the holes at zero electric field, and beta is the hole Pulle-Frankel factor. The activation energy for pentacene material is reported by many researchers in the range of 0.005 to 0.050 electron volt. Therefore, it is considered as 1.792 into 10 raised to power minus 2 electron volt. And the value of NTA is 2.5 into 10 raised to power 18, and the value of NTD is 10 raised to power 18. And the value of WTA is 0.129 and the value of WTD is 0.5. However, the energy band gap and the hole affinity are 2.2 electron volt and 2.8 electron volt respectively. Effective density of state in both the conduction band and the valence band is considered as 10 raised to power 21 per centimeter cube, whereas the relative permittivity of the pentacene is 4. Next is the Atlas code determines the operational biasing condition for the simulation, such as BGS and BDS, to obtain the electrical characteristics of the device under analysis. One more thing I have missed out in organic defects. If you specify the parameter dopant on the organic defect statement, then the trap density defined using Na, sigma A, Ea, Nd, sigma D and Ed parameter will be used in dopant singlet excitation calculation. Organic defects active the band gap defect model for organic polymer materials and set the parameter values. This model can be used when simulating organic polymer device using the organic display and organic solar modules. You can use fast statement and uniform statement or continuous statement. Continuous statement specify that the continuous defects module will be used. D file specify the donor state density output file. Doping dot percent specify the doping percentage. EA specify the energy shift between the intrinsic and dopant states for acceptor like traps. If you want to know more about the organic defects, please follow the Atlas manual for organic defects parameters. When you run this program, you will get two files. One is the structure file and one is the log file. This is the structure file. This is the pentacene material. This is the Al2O3 material. This is the gold metal contact for drain and the source. And last one is the aluminum material. And this is the log file. This is the P-type organic field effect transistor. This is the output of top contact organic field effect transistor structure. You can carefully note down this code and run on your computer. You will get the same log file as I am getting. I have designed one more code for the bottom contact organic field effect transistor, and run this code. We will get the structure file for the bottom contact organic field effect transistor structure and one structure file for the top contact organic field effect transistor. You can see in the figure when the source and the drain are in the top contact structure, and in this the source and drain in the deep of the pentacene organic semiconducting layer, and we can say that the bottom of the pentacene layer, and in this structure drain and the source contact are the upper of the organic pentacene structure layer. Figure show the top contact and bottom contact organic field effect transistor representing current flow lines from source to drain. In case of bottom contact structure, the current line flow from source to drain contact is this one. When we talk about the top contact structure, The current flow lines from source to drain contact is this one. Next, I will show you transfer characteristics of top contact and the bottom contact organic field effect transistor device. Figure show the transfer characteristics as a function of thickness of organic semiconducting layer for top contact and the bottom contact structures at gate to source voltage is -3 volt. This is the transfer characteristic for the top contact organic field effect transistor structure. This is the transfer characteristics for the bottom contact organic field effect transistor structure. You can observe in the figure when you change the thickness of the organic material in the organic field effect transistor, the variation in the drain current. In the top contact, as you increase the thickness of the organic material in OFETs, the on current start increasing and the off current remain almost constant. In comparison with the bottom contact organic field effect transistor structure, as you increase the thickness of the organic material in OFETs, the on current start increasing in the same manner, but the variation in on current is large in bottom contact structure as compared to top contact organic field effect transistor structure. The variation of threshold voltage and the subthreshold slope also observed in the figure. My dear friend, this is end for today. If you have any query, please mail to me. Mail ID is given in the description. I am happy to help you. Please stay tuned for more interesting video. Till then, like, subscribe and share my channel. This would give me a great motivation. Thanks for watching. Bye bye. Take care.